Thank you really for the introduction. And hello, everyone. My name is Guangyu Bao, and I graduated from McGill University this year. And I recently joined a startup company called SanaHeal in Boston. And today I'm mainly going to present the hydrogel technologies that I developed during my PhD for addressing some of the pressing challenges in the hydrogel fabrication and integration. So in the current tissue engineering paradigm, and people have been engineering the biology, the material, and tissue architectures. Once the elements are there, the first step is to fabricate. The first step is to fabricate engineer tissues or the in vitro models, and then to integrate them with the human body, either as a wearable device or as implants. In the recent years, the extrusion-based bioprinting has become a go-to technology for fabricating the cell-laden hydrogels with complicated geometries. For example, the organ-sized construct, such as the heart shown here, is a demonstration of how powerful this technology is for the shape control. However, one of the limitations for the popular extrusion-based bioprinting is its resolution, which is usually greater than 100 micrometers. And the technology is not there yet to mimic those of the tens of micrometer-sized features, such as the pores in the lungs and also in the kidneys. And at the same time, the human tissues are viscoelastic. No matter if it is the ECM or the soft tissue or even the skeletal tissues, and they all behave both solid and fluid-like. So it is extremely difficult to mimic those hierarchically porous structure and the viscoelastic nature of using the bioprinting. And previously, our lab has provided a solution to improve the printing resolution and expand the tunable range of viscoelasticity using the bioprinting. We have used a biopolymer called chitosan to achieve this goal. The chitosan is a polysaccharide that can be derived from the nature, such as the shell of the shrimp, the crab, or even the mushroom, such as the cell wall from the fungi. And the chitosan has a primary amine groups, and when it is exposed to solutions with a pH lower than 6.5, and this primary amine groups is positively charged, and when the solution and a pH of the solution changes above this value, and the primary amine groups will deprotonate and become neutral, which allows the chitosan to form the hydrogen bonding within the chain themselves, which enable the self-cross-linking mechanism. So we use this property to bioprint viscoelastic hydrogels with the micrometer-sized pores for the first time. And the bioink we use contains the chitosan and the polyethylene glycol. And we use the embedded printing technique to complete the bioprinting. And if we take a close-up view, and after the printing, and we can release the salt pre-embedded inside the supporting matrix, and they can diffuse into the weakly acidic bioink solution to increase the pH. And upon the neutralization of the pH, the chitosan will phase separate to form a polymer-rich and polymer pore phase. And this polymer pore phase will become the interconnected pores, which because it mainly comprising the water, and the inside the solid phase, the polymer-rich phase, and the chitosan will be stabilized through the hydrogen bonding between the chain themselves, and they will form the porous chitosan scaffold. And by tuning the PEG concentration within the polymers within the bioink, we can also the PEG basically acts as a spacer among the crosslinks, which can tune the cross-linking strength, which corresponding to different viscoelastic response. And after labeling the biopolymer with a fluorescent label, we can use a confocal microscopy to visualize its internal structure. And for the standard covalently cross-linked hydrogels, we cannot observe any pores because the pores is smaller than the resolution of the microscope. And similarly, from the SEM, we cannot observe any pores either. But the hydrogels made using our method can form the porous space. And similarly, in the SEM, you can also see the interconnected pores. And because they are highly porous and has interconnected pores, and the hydrogels can be compressed, and the water can come out of it. And after the release of the strain and the rehydration, and they can resume to its original shape. And the stiffness of our hydrogel can be controlled using the pH by tuning the pH within a very small window, and we can tune the storage modules from hundreds of Pascal to tens of kilopascal. So it's basically covered the entire range of the stiffness of soft tissues. And by maintaining the pH at a similar level, and simply by changing the PEG concentration within the original Bio.Eng, and we can maintain the storage modules the same, but orthogonally tune the viscoelastic response. In here, we tune the stress relaxation time from thousands of seconds to tens of seconds, which also cross a wide range. And although this material and fabrication shows promise, and we realize there are two things that needs to be improved. The first is the fabrication method. In practice, doctors always prefer simple methods such as the needle syringe injection instead of using the implantation through the open surgery. And the second one is the toughness of the bioprinted hydrogels. And although they show tunable mechanics, the hydrogels are brittle and not suitable for repairing the mechanically active tissues. So later on, we have modified the formula and the fabrication method to overcome these challenges. And we aim to improve the delivery method and the mechanical stability of the resulting hydrogel while maintaining its cytocompatibility and also porous nature. So to achieve this goal, we have, in addition to the chitosan, we have introduced a second polymer, the glycochitosan, to the polymer solution and to reinforce the hydrogel through the double network design. And we mix the two polymers. So we first put the polymer solution in one syringe and the cross-linkers in another syringe. And by mixing those two solutions, and first the mixture, the pH is neutralized. And in this case, at this stage, we can mix the cells inside and inject it into the human body. And after the injection, because of the neutralization of the pH, the chitosan will phase separate from the solution, which you can observe from here. The color changes from the transparent to translucent nature, which it is caused by the phase separation of chitosan and form a porous network within the hydrogel. And within the solid phase of the scaffold, and the glycochitosan content will be further cross-linked by the dialdehyde groups and to form a covalent cross-link network, which can further reinforce the mechanical stability. So in this case, we created an injectable, porous, cytocompatible, and tough hydrogel. And since the pores within is interconnected, and the media can be perfused through our hydrogel that has been pre-injected into the microfluidic channels, but the media cannot perfuse through the conventional hydrogel, which is covalently cross-linked hydrogels. And when we measure the permeability of our gel, it is very similar to some of the tissues, such as the vocal fold and also the bone. And the value is orders of magnitude higher comparing to the standard hydrogels commonly used hydrogels. And meanwhile, the pores did not impede the mechanical toughness, so our hydrogel can be tuned to be even 40 times tougher comparing to the covalently cross-linked hydrogels. And from the photo, we can see that our hydrogel is highly stretchable. However, for the standard hydrogel, it ruptures at very small strain. And we also tested the stability of our gel in a vocal fold-like environment, which is arguably most mechanically challenging environment in the human body. So we use a high-speed camera to shoot the real vocal fold during the phonation. And this is we create a mechanical environment to mimic this mechanical movement inside the vocal fold, which is very similar. And in here, we also show the movement in here. If you can hear the sound, the sound is very similar to the sound level of the human voice. And because it's moving at high frequency, you cannot really see the movement. But the hydrogel is located in here. And at the same time, we applied the 6 million times of mechanical stimulation while doing the cell culture. And after the cell culture, we can see that for the standard hydrogel, they are either broken into completely broken or broken into pieces. But for our hydrogel, it maintained the whole piece, especially in the center where the stress is most concentrated here. And in terms of the biological performance, and the cells could not secrete much collagen within the nanoporous hydrogel, which is commonly used in the field. But in our porous hydrogel, even without the mechanical stimulation, it already promoted the collagen synthesis by the cells, which is the green, standing by the green color. And with the help of biomimetic mechanical stimulation, the vocal fold fibroblasts we encapsulated within the scaffold even secrete much more collagen comparing to the other two situations, which means that for our porous and tough hydrogel could potentially improve the therapeutic outcome. And after the fabrication, and the next step is the integration. So one of the most challenging integration situation is to adhere the biomaterials to the bleeding site for hemorrhage control. And every year, around 2 million people worldwide lose their lives because of it. And in emergency, it is estimated that more than 30% of the deaths in trauma are caused by the uncontrolled bleeding. And bleeding also occurs very commonly in the surgical settings, as evidenced by the high using rate for the hemostatic agents during the surgeries. For example, the number for the spine surgery even goes up to 80%, which is super high. And despite of the rapid advancement in medicine, and the effective bleeding control is still an unmet challenge. And when we look at the status quo, the conventional techniques such as sutures, forceps, and staplers, they are used to close the bleeding site, but the outcome are often undesirable. And those techniques are also technically challenging to master. So biomaterials are often needed to assist the bleeding control. And in general, there are two types of hemostasis. The first one is called the biochemical hemostasis, where the biomaterials with the ability to promote the blood coagulation can be used. And such a strategy is relatively slow to take effect and not very effective for patients with the coagulation diseases if they are on anticoagulation drugs. And the other strategy is mechanical hemostasis, where the biomaterials are used to physically seal the bleeding site. And these materials should robustly stay at the wounds through the integration with the tissue. And the strategy, this strategy does not rely on the coagulation cascade, so potentially they are more suitable for a broader range of scenarios. But most existing sealants are mechanically brittle and difficult to adhere to the bleeding site. And recently, people have found out that the key to achieve tough adhesion is between the hydrogel and tissue is to have an adhesive interface and a tough adhesive matrix. And as can be seen from the equation in here, the total adhesion energy is the summation of the energy dissipated from the adhesive hydrogel, and also the individual bonding strength from the at the interface. And so to amplify the energy dissipation, we can use a tough hydrogel which has a dissipative mechanism, such as the hydrogel containing the cytosine network, which has the hydrogen bonding and which can amplify the background hysteresis. And also at the interface, we can use some covalent chemistry crosslinks, such as the carbodiamide chemistry, to covalently fix the hydrogel to the tissue to ensure a reliable white interface. However, this design does not work well on the blood-exposed surface. The reason is that the blood contains a large amount of cells, which act as individual barrier to prevent intimate contact between the adhesive and the tissue, unless a compressive force is applied to squeeze out those individual blood. However, applying the compression is not always possible or desirable for delicate wounds or non-compressible hemorrhage situations. So to overcome this challenge, we have created a hydrogel called the liquid-infused microstructured bioadhesives. So based on the tough hydrogel matrix that we have developed before, and we use freeze drying to make the matrix porous and dry. And we fill this porous and dry matrix partially with the adhesive liquid while left some of the pores open. And when this type of bioadhesive is attached to the blood-covered tissue surface, and the blood can be quickly absorbed through the capillary suction by the empty pores. And at the same time, the adhesive will deliver the adhesive functional liquid to the interface to facilitate the integration. And the absorbed blood within the matrix can be further coagulated to form the blood clot, and which can further enhance the sealing effect. And here is the SEM image showing the porous space of bioadhesive matrix. And although they are highly porous, but they are still very stretchable, and they can be stretched more than at least 6 times of its original length without rupture. And the toughness is also very high. It's very similar or even exceed most of the soft tissues in the human body. And in here, we calculated its pore sensitivity, which is around 5 millimeters, which means that any defect smaller than this range will not be sensed by our adhesive matrix. And consider the pore size within our matrix is a couple of hundreds micrometers, which is significantly lower than this value. So which means the pores and the porous structure within our matrix does not affect its mechanical property. And the reason we want to build the microstructure is because the microstructure can enable the rapid liquid absorption. So by using the same material system, but making those into 3 different configurations. The first one is porous and dry. The second one is dry but not porous, and the third one is not porous nor dry. And when we attach those 3 configurations on a water reservoir, and the porous and dry matrix can uptake the water much quicker comparing to the other 2 configurations. And when we look at, we also measure the adhesion energy kinetics. So for our porous and dry matrix, it starts to form the adhesion within 15 seconds upon contact with the wet surface. However, for the non-structured bioadhesive, which is not dry and not porous, it doesn't form any adhesion within 400 seconds upon the contact. And if we calculate the effective diffusivity, our porous and dry adhesive shows a much higher effective diffusivity comparing to the diffusion-driven non-porous counterparts, which also explains why our adhesive can so effectively remove the interfacial barrier, which is a liquid on top of the tissue surface. And unlike many bioadhesives that require the compression, our adhesive can adhere to a variety of the blood-covered surface without the need for applying the compression. And for some dedicated surface, such as the gelatin in here, and even applying the compression can collapse the substrate. And here in this demo, you can see that we first put the blood on top of the porcelain heart and gently placed our adhesive on top of the heart. And during the peeling, you can see the adhesion formed very quickly and also strongly on the heart surface. So by leveraging the adhesion and also blood coagulation, and we have used our bioadhesive to treat non-compressible used as a non-compressible hemostat to treat the non-compressible hemorrhage. And in a rat model, we have created a volumetric loss on the liver and applied the hemostats. And comparing to the commercial product, Surgiform, which is a hemostatic gelatin sponge, and our adhesive reduced the blood loss and stopped the bleeding much faster comparing to the commercial product. And after the implantation for 2 weeks, and you can appreciate that our adhesive has induced a much thinner fibrotic capsule and also a very mild foreign body reaction and the immune response and a much lower allergic react. So the biocompatibility of our bioadhesive outperformed the commercial product in all the aspects that we benchmarked. And the adhesive is also effective in stopping the deep incision wound. For example, it reduces the blood loss significantly comparing to the standard gauze treatment, the commercially available combat gauze, which is used in the military, and also the non-structured bioadhesive counterpart. And also in the large animal models, it also reduced the blood loss comparing to the standard gauze treatment by more than 35%. So it is very effective in both small and large animal bleeding models. And to summarize, and we have applied a transdisciplinary approach to address the challenges to the for the hydrogel fabrication and integration. And by synergizing the material mechanics and bioengineering, and we have designed the materials and method that achieve outstanding performance. And the efficacy has been also validated in using the in vitro, ex vivo, and validated in the small and large animal models. And in the end, I would like to thank my supervisors, Professor Luc Mongeau and Jianyu Li, and the colleagues from our 2 labs for their continued support. And I would also like to thank our collaborators for making all those projects possible. And of course, I would like to thank the funding agency for supporting our study, and also the EASF committee for inviting me today for the presentation. And thank you for listening. And I would be happy to take any questions from here.